Hey, good morning. How was the exam? Yeah. All right, we'll find out. Yeah, we'll find out. I was sending the Scantron sometime this morning, and we'll probably get the results back maybe Friday, maybe. Okay. All right, we're going to look at section 16.4 today. The topic of this section is Green's theorem. This is named in honor of an English mathematician, George Green, who lived from 1793 to 1841. So relatively late as far as calculus theorems go. A couple interesting things about this guy. He only received 1 year of formal schooling when he was a child, between 8 and 9. Everything he knew was, almost everything he knew and contributed was entirely self-taught. In fact, he didn't get admitted into University of Cambridge until when he was around 40. When he was 40, he got admitted, and he didn't get his bachelor's degree until 46. So, a couple interesting things about this guy. Anyway, so what does the theorem say? The theorem gives us a connection between a line integral and a double integral. Over a region. And you'll see examples today that oftentimes this will simplify the calculation of a line integral tremendously. So a couple things to lay down before we get to the theorem. Let's assume we have a two-dimensional vector field. And we'll let the vector field's components be P and Q, Pi plus Qj at every single point. And we'll just say we're traveling on a path that's given by, very generally, x comma y. So some kind of path we're traveling on xi plus yj. Okay? Very, very simple groundwork and assumption here. Then the line integral f dot dr, notice turns into a slightly different form. So f is pq dotted with dr. Dr is just simply the differential of this thing, which is dx comma dy. Right? So that's f. This is dr. So at the end, this f dot dr can be written in another form if we have this kind of assumption. It looks like p dx plus q dy. Okay, so even though this thing doesn't look anything like f dot dr, in fact, they're the same thing for a vector field pq and some kind of path xy. Green's theorem states that, well, let me write this on the next page. That this line integral p dx plus q dy is equivalent to a double integral over some region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. A couple very important requirements for this thing to hold true is that if we require C to be a simple closed curve, traversed once around in the counterclockwise direction. And this counterclockwise direction is often said to be positively oriented. So we define the counterclockwise direction to be positive direction, just like how we define the angle theta for a polar angle, for polar coordinates. And if that's true, then D is the region enclosed by C. Okay, so a couple definitions of these terms. We've seen the term simple before. When you say a curve is simple, it means that the curve does not cross over itself. Closed means it forms a loop. So we're talking about C being a loop, but it doesn't cross over itself. Other than that, it can have any kind of shape. Okay, so let's imagine we have just some kind of very general C. Let's say like that. Now we're going to go once around in the counterclockwise direction. It actually doesn't matter where we start and where we end, but let's assume we start here and end here, going once around counterclockwise. And this shaded region here, this is D. So Green's theorem says that we can do a line integral, the long way, the old way that you knew how to do, by parameterizing the curve and then doing the integration, or you could integrate this over this region D. Proof of this theorem is complicated, and that's really understating it. If you're interested in seeing for a very simple version for a subset of the condition, see pages 1055, 1086. Simple version on page 1085 to 1086 in the book. Even a simple version is kind of lengthy, but take a look at it if you're interested in seeing why this thing at the top is true. Okay? There are other commonly used notation for line integral around the loop. Sometimes you see this circle in the middle of the integration sign. When you see that circle, that means we're integrating around some kind of loop. Sometimes you even see the circle with an arrow very explicitly indicating the positive direction. And you see this notation quite a bit in physics and engineering. In many of the applications, you see this very, very often. Okay, so let's do an example here. And we're going to calculate the line integral two ways. The old way, when we parameterize the curve and then calculate the line integral properly, and then compare to what happens if we use Green's theorem. Let's look at this line integral here. X minus y dx plus x dy. Where C is a circle, radius 1, centered at the origin, traversed once in the counterclockwise direction. Okay, we'll calculate this in two ways. First, we'll parameterize the curve and then calculate the line integral the way that we're used to doing. Call that A, call this B. Okay, I'll compare this and we'll use this to convince ourselves that Green's theorem in fact works. All right? Okay, so first the old way, let's draw our circle. We want to go around this circle radius 1, centered on the origin, and we're going around this in the counterclockwise direction. Okay, so first let's parameterize this. We're going around the loop, so it really doesn't matter where we start, where we end. But let's assume we start here, just for convenience. Let's assume we start and end on this spot. So if we assume that, then parameterizing this is pretty simple. We're talking about a circle, so cosine and sine will do the job for us. And we'll just let t go from 0 to 2 pi. Right? T is equal to 0 puts me here. T is equal to 2 pi puts me back here. So that completes my one loop in the counterclockwise direction. So this means that x, in my line integral, anywhere I see x, I'll replace that with cosine of t. Anywhere I see y, I'll make that sine of t. And anywhere I see dx, I'll change that to negative sine t dt. And anywhere I see y, dy, I'll change it to cosine of t dt. Right? dy is the derivative of y, of course, the differential. And dx is a differential of x. So this line integral we're trying to do becomes an integration from 0 to 2 pi x minus y times dx plus, oh, I'm missing something, x dy, sorry. Here's an x plus x dy. Okay, let's simplify this a little bit. 0 to 2 pi minus sine cosine plus sine squared plus cosine squared dt. And of course, cosine plus sine is, cosine squared plus sine squared is 1. So this is 1 minus sine t cosine of t dt. And this is pretty easy to integrate. For the second part here, do a substitution. The first one, of course, turns into t. So once you integrate this, you get t minus 1/2 sine squared of t, 0 to 2 pi. So this turns into 2 pi. Okay, so nothing new here. So this is what we already know how to do, the way we've done before, and we get a 2 pi. Now let's use Green's theorem and to see that we indeed get the same answer. And we'll compare the amount of work we have to do to get to the same answer. And you can see the usefulness, in many cases, of Green's theorem. And just as a reminder, Green's theorem says p dx plus q dy, line integral, is equal to double integral over the region that C encloses of the partial of q with respect to x minus the partial of p with respect to y dA. And we're still talking about the same C. Circle radius 1 going around counterclockwise. And now we have this region that we're going to integrate over. That's a circle. Okay? So let's see. We get double integral over D. The integral we're trying to do, let me rewrite it, bring it back here, x minus y dx plus x dy. So this is p, and that's q. P is the one that's attached to dx, and q is the one that's attached to dy. And this is the integral we're trying to do. So let's calculate what's inside here. Partial q, partial x. 1, right? Minus partial p partial y minus 1. So we're integrating 2 over this circle dA. This is a circle, so it makes a lot of sense if we go to polar, right? Let's go to polar, 0 to 2 pi for theta, and 0 to 1 for r. We're integrating 2, and dA in polar is r dr d theta. So we get 0 to 2 pi. Integrating 2r gives me 2r squared, 0, 1, d theta. That gives me a 1. 1 d theta is theta. 0 to 2 pi is 2 pi. So exactly the same thing. And now you can see for many cases, if the region is easy to describe, using Green's theorem can cut you a lot of work. You get the same answer in a lot less amount of work and time. Questions on this example? Yeah. All right. This is partial q partial x right here. And this minus 1, this is partial p partial y. So the integral that we were trying to do, p dx q dy, at p is equal to x minus y. So the partial derivative of that with respect to y is a minus 1, right? And then partial of q with respect to x is a 1. Good. Other questions? What do you think if we travel in the clockwise direction? What do you think? If we go in the negative orientation? Yeah, that's exactly it. You end up getting a negative 2 pi. You get the negative of whatever you would get if you had gone in the counterclockwise, the positive direction. So counterclockwise is always positive. So this is positive. So whatever you get there would be the same number as if you had gone the opposite way, but they would have different signs. So if we had gone clockwise on this loop with the same integral here, we would get negative 2 pi. Okay? Okay, let's do a couple more examples using Green's theorem. Let's find f dot dr, the integral f dot dr, if f is equal to x cubed y squared I plus 1/2 x to the 4th yj and c is from the origin to 2, along the curve y is equal to x squared minus x. And then back to the origin along the curve y is equal to x. So we're going to be moving along in the middle of this vector field, x cubed y squared I plus 1/2 x to the 4th yj. Now we're going to travel on this curve, on this path. So I'm going to go from 0 to 2, 2 along this thing. It's a parabola. And then back to the origin along a line. Let's make a sketch of that. Starting point is here. We have a middle point at 2, 2. First, we want to go along a parabola, x squared minus x. It looks something like that. And then we're going to travel back to the origin along a straight line. First thing we have to make sure is that we determine the sense of the orientation, whether we're traveling in a positive orientation or a negative orientation. So for here, what do we have and why? Look at the direction of this path here. Is it positive or negative? Positive, why is that? Counterclockwise, exactly, yep. So this means that we're going to end up just calculating using Green's theorem. If I were going the negative direction, I would put a minus sign in front of the double integral to account for the fact that we're going the negative direction. Okay, so now once you establish which direction you're going, we have this right here. We can determine D pretty easily. Because we're going to use Green's theorem now, we really don't have to worry too much about how we parameterize that path. Right? We don't have to worry about that. We just say it's x, y, whatever x and y happen to be. Then, of course, x dr turns into dx dy. So the line integral f dot dr we're trying to calculate is the vector field x cubed y squared I 1/2 x to the 4th yj dotted with dr so we get x cubed y squared dx plus 1/2 x to the 4th y dy. So this puts us in the familiar form of p dx plus q dy, where this guy here is p, this here is q. Okay? And Green's theorem says that this is equivalent to a double integral over the region D, which we'll figure out in a little bit, of partial of q with respect to x minus partial of p with respect to y dA. So now we just have to describe a double integral over this region D. And that looks like it's best described as a type 1, right? Let x be bounded from 0 to 2, y be bounded from x squared minus x below to x at the top. And then we integrate over qx minus py. Here's q. Let's take the partial with respect to x. We get 2x cubed y minus py. Take that with respect to y. 2x cubed y. And then dA, we're doing x last, so this starts as dy and then dx. And guess what happens? We get a 0. Right? Look at this thing right here. It's a 0. So we could have parameterized the curve with two different sets of paths, like we've done in the past, and calculate all of those line integrals. We would still get a 0. In this particular case, when we go to Green's theorem, that 0 falls out basically right there, right? Basically no work involved. We end up getting a 0. So here, an interesting thing we noticed here the integral is 0 because q, partial of q with respect to x is equal to partial of p with respect to y. What does this mean for the vector field if this is true? Do you remember? Say it again. Conservative, very good. This is true if the vector field pi plus qj is conservative. If f is conservative, then the line integral f dot dr is the same as the gradient of some potential function, little f, dotted with dr, which by the fundamental theorem of line integrals remember, the path really is completely irrelevant if the vector field is conservative. All that really matters is the final point and the initial point. So notice you don't even need to know what little f is. If you start and end at the same location, this will always be 0, regardless of what little f is. And that's what we got going on here. We started and end at the same point over a conservative vector field. So that's a very important thing that I want to keep in mind. If f is conservative, then a line integral over that vector field f in a closed loop, meaning we start and end at the same place. And Green's theorem tells us the same thing because we're integrating the difference of these two things using Green's theorem. If the vector field is conservative, these are always equal. Therefore, you integrate at 0. So that's a very nice thing to know. In the future, when you do these integrals over a vector field, one good thing to check right away is whether the vector field is conservative. Then, if it's conservative and you're going around in a loop, you get a 0. All right, let's do one more example. Let's find the work done by the vector field, which would be a force vector field. Two xy cubed I plus 4x squared y squared j moving a particle from 0, 0 to 1, 0 along the x-axis. Then to 1, 1 along x is equal to 1. Then back to the origin along the curve y is equal to x cubed. All right, let's take a look at how we're doing this. We're starting at 0, 0, going to 1, 0. And we're going to move along the x-axis. So that's the first leg of the trip. Once we got there, we're going to go up to 1, 1. Along the curve x is equal to 1. So that's the second leg of the trip. Then we're going to come back to the origin along y is equal to x cubed. Finally, back to the origin that way. And this is positively oriented, right? It's counterclockwise, so it's positively oriented. First thing first, we don't have to do anything if we know this is conservative, so let's check that. If it's conservative, the answer is 0, like we saw in the last example. If it's not, then we're going to have to use Green's theorem to calculate. So let's see. Partial q, partial x. Q is the one attached to j, of course. Is 8xy squared. Partial p, partial y is 6xy squared. So it's not conservative. That's okay. Then we just have to apply Green's theorem now. Integrate over the region D, the difference between qx and py, dA, and the region that's enclosed by this path, C, up here, this almost triangular kind of region, it can be described as a type 1 or type 2. Let's just stick with type 1. Let x be bounded by 0 and 1. And let y be bounded below by 0 and bounded above by x cubed. Then we integrate the difference of qx and py. dA, we're doing y first, so dy and then dx. And this doesn't look terribly difficult. This is 2xy squared dy dx. Zero, 1, y first, so 2/3 xy cubed. Y is 0, y is x cubed, dx. So this turns out to be, this will be x to the 9th, x to the 10th, 2/3 x to the 10th, dx. Which will give me 2 over 33, x to the 11 from 0 to 1, and that just turns out to be 2 over 33. So there we go. The work in doing that, going around in that path, in that vector field, is 2 over 33. Now, if you were doing this the old way, then you would have to split this into 3 different paths. C1 is that, C2 is that, C3 is that, and then integrate 3 separate integrals of f dot dr. Not terribly difficult, but takes comparatively much more time. Okay? So Green's theorem is a very powerful tool if you have the right conditions. A closed curve, a simple curve, meaning that the path cannot cross over itself. If at any point the path crosses over itself, then Green's theorem is not going to, Green's theorem as the way it is stated here is not going to give you the right answer. We have to handle that differently. But for a simple and closed curve here, Green's theorem will give you a lot of savings in terms of work and time. Okay, that's it for today. We'll wrap it up a little bit early today. See you again Friday.